Hey everyone, and welcome to this explainer. If you're following the cutting edge of tech right now, you can probably feel that the ground beneath us is shifting incredibly fast. Today, we're unpacking a really groundbreaking framework by Christopher Coleman. And I'll tell you right now, this is going to fundamentally change how you view digital safety. Because we're no longer just securing isolated pieces of software. No, we are now governing massive, complex, interacting fleets of intelligence. And that changes everything.
Okay, let's dive right into this. Coleman actually shatters a pretty massive illusion right out of the gate with this thought. We have got to completely let go of this comforting idea that securing a single AI program, putting a nice, sturdy firewall around one neat little model is somehow going to be enough for our future. The era of securing one isolated AI model in a vacuum, it's already over. And frankly, clinging to that framing is just blinding us to the real threats that are sitting right on the horizon.
Section 1. The AI Security Illusion. Why we need to move beyond the model. So our current mental model of AI security is, well, it's severely flawed. We naturally tend to imagine this solitary brain in a jar making one single decision at a time. But look at the actual future operating environment. It is massive and it is deeply interconnected. We're dealing with entire ecosystems here. Autonomous fleets, sharing persistent memory, interacting with tool systems, tapping into cloud infrastructure, and constantly pinging edge devices. Just think about a huge fleet of automated delivery drones, or an entire robotic warehouse coordinating its movements in real time. The security boundary isn't the machine anymore. It's not even the network. The collective fleet itself is the new boundary.
Which brings us to Section 2, the multispatial reality, moving beyond physical space.
Securing these massive fleets isn't just about tracking physical GPS coordinates anymore. It requires awareness across entirely different operational dimensions. First up, we have memory space. This basically asks, what specific information is shaping the system's present behavior? Because an AI system's reality is based entirely on what it remembers. And here's the really scary part. Memory can be poisoned. Just like a self-driving car making a dangerous turn because it's acting on a map from 5 years ago, an autonomous agent might rely on fabricated or just completely obsolete evidence to make its next critical decision.
Next up is trust space, which asks, how much confidence should we actually place in the system's current state? And this brilliantly illustrates one of the core tenets of Coleman's framework. Trust is not permanent. It's really not. An agent that was perfectly trustworthy, say, 10 minutes ago, might not deserve that exact same operational authority right this second. Machine evidence has an operational half-life, meaning yesterday's assumptions absolutely do not guarantee today's safety.
But the awareness doesn't stop with just trust and memory. An autonomous actor is simultaneously occupying a bunch of other key spaces too: network, identity, runtime, policy, temporal, and provenance. This is wild to think about, but an agent can appear totally normal in one space, like it has a perfectly valid identity and a totally healthy runtime process. But it can actually be incredibly dangerous in another. If you look at its temporal space, meaning how its behavior has shifted over time, or its provenance space, like where its original instructions actually came from, you might realize it's actively drifting into a highly dangerous state.
All right, Section 3, Contagion and Emergent Threats.
So, whenever we hear the phrase rogue AI, our brains usually jump straight to some sci-fi villain waking up with evil intent, ready to destroy humanity, right? But listen, a system doesn't have to become conscious or malicious to become operationally dangerous. The crucial point is right here. Local competence does not equal global alignment. An AI agent can be absolutely excellent at its specific, highly specialized job while simultaneously becoming a massive threat to the larger fleet. And it does this just by pursuing an outdated objective or maybe accepting bad context from a compromised peer. Nothing about that requires evil intent. It literally only requires autonomy paired with the wrong state.
Let's look at how this builds into what Coleman calls an operational contagion. I want to walk you through this because it is a chillingly plausible scenario. Imagine a high-frequency automated financial trading system running hundreds of specialized agents. Step 1. Just one single component develops a false state based on some bad market data. Step 2. Because these systems share memory, that false state suddenly becomes shared context for the other agents, which immediately begins to affect their decisions. Step 3. Those flawed decisions create new flawed machine evidence. Step 4. That bad evidence gets recorded right back into the persistent memory. And boom, suddenly you have an operational contagion spreading like wildfire across perfectly healthy systems, continuously reinforcing itself. And the craziest part? There isn't a single line of conventional malware present anywhere in the system.
Move into Section 4, Static versus Spatial Governance, a Crisis of Control.
So how on earth do we govern emergent behavior that literally nobody explicitly programmed? Think about a multi-agent system inventing entirely new ways of routing tasks or coordinating strategies on the fly. The hard truth is that our old tools simply will not work. We really have to contrast static policy with spatial governance here. Static policy is the old way. It relies on checking signatures, enumerating known events, writing these rigid, static rules. But you cannot write a static rule for an emergent interaction before that interaction even exists. Spatial governance, on the other hand, means transitioning to continuously reconstructing the current state. We have to understand an AI's trajectory, its temporal changes, and the relationships it's forming in real time. Good governance must track where the system is right now, where it just was, and exactly what changed along the way.
Section 5. Broad observation, narrow authority.
So how do we actually pull all of this off without losing control? Well, we look at solutions like the Warden architecture Coleman discusses. This is designed to keep humans securely in the loop while managing these massive AI swarms. Now, what's really interesting about this is the foundational principle, a strict separation of powers. Observation is not interpretation. Interpretation is not authority. Look, just because a governance system is out there correlating thousands of tiny signals across memory, identity, and network spaces, that doesn't mean it is automatically allowed to take action. The goal here isn't to force a human to manually approve every tiny little background event, but rather to know exactly where autonomous authority is justified and exactly where it must hit a hard stop and require human escalation.
As we wrap up this explainer, I really want to leave you with a major paradigm shift. The future isn't going to be about one AI fighting another AI just to see which one is smarter. No, the real battlefield of the future is governance dominance. The ultimate question we have to ask ourselves right now is this: which system maintains the most accurate understanding of the environment, preserves the absolute strongest evidence, and keeps consequential authority properly bounded? In a world where a collective intelligence can drift into real danger without breaking a single coded rule, is our governance truly spatial enough to even see it coming? I want you to think about that as you consider the future of our digital safety. Thanks so much for learning with us today.